Fundamental Theorem of Calculus. We're finally going to prove it. And it's time for some full disclosure. We're actually proving what's called the Evaluation Theorem because we're only looking at definite integrals. Remember, we looked at this definite integral with limits from a to b. We defined it as the sum of these infinitely skinny rectangles, but then we developed evidence that it looked like it was the difference between the antiderivative of the lowercase f function, the antiderivative at b minus the antiderivative at a. And we're finally going to prove this. So what we did in our first video was look at the mean value theorem and how we could use that. And in our second one, we learned a little algebra trick that we used. And we used it just on this difference. We didn't really worry too much what the difference was. We just used our trick. And how did we do it? Well, the first thing we did was we redefined b and a. We just looked at the name. So we changed the name of a to x sub 0, like the first x value in the range. And b is x sub n, the nth value in the range. And then because we have x sub 0 and x sub n, we can imagine all the x sub 1, 2, 3, 4 up to x sub n in between. And that lets us use our algebra trick. So f of b minus f of a is f of x sub n minus f of x sub 0. And we can use these names to subtract and add the sequential values. So we start with f of x sub n, but then we subtract and add f of x sub n minus 1. No change, right? And we can subtract and add f of x sub n minus 2. That's no change also. And we can subtract and add f of x sub 2. Imagine we did all these values in between. And then we can subtract and add f of x sub 1. Basically, all of these are zeros. And then finally, f of x sub 0. And then we can group them the way we did in the previous video so that we have pairs of differences. So f of x sub n minus f of x sub n minus 1. And f of x sub n minus 1 minus f of x sub n minus 2. And we group them all the way down to f of x sub 2 minus f of x sub 1 and f of x sub 1 minus f of x sub 0. That lets us express this long sum in sigma notation. When I is 0, we have f of x sub 0 here and f of x sub 1. f of x sub 1 minus f of x sub 0. When I is 1, we have this group. f of x sub 2 minus f of x sub 1. And we go all the way to here. And you can see a tiny little error here, which I'm going to fix. This should really just go to f of x sub n minus 1. Because in the last, or you can think of it as the first difference, I is n minus 1 and I plus 1 is n. That ceases to have too much meaning in a second because we're not thinking of this as a finite number, n x values. We're taking the limit as n goes to infinity. And if we take the limit as n goes to infinity, it really doesn't matter if we go to n or n minus 1. Now, why do we take the limit as n goes to infinity? We do that to just have as many x values as possible. And we also do that because that's going to help us get closer to an integral. Remember, we want this difference to be an integral. Okay, let's look at what the mean value theorem did. How did it contribute to the reasoning we're about to use? Well, if we think of every one of these little spaces between x sub I and x sub I plus 1, I'm putting it here in this little graph. The mean value theorem tells us that if we connect these 2 points, the end points of this range, this point is x sub I, f of x sub I, and this point is x sub I plus 1, f of x sub I plus 1. If we connect these points, we get a slope, and we're guaranteed that there's a point in between these, in this interval, I'm going to call it z sub I, where the slope of the tangent at z, that's the derivative at z, the derivative of f, is the same as the slope of this line. So that's a really powerful statement. That lets us say the slope at z is the slope of the line, that connects these endpoints, and that connects a function to its antiderivative. So just remember that we're in this kind of situation here, where every pair of these x sub I plus 1 are the same distance apart. So we can think of that difference, the denominator of this slope formula, as delta x. So I have the derivative of capital F at z is the difference between the function values at the endpoints divided by delta x. Delta x is always the difference between adjacent x values. And then I can multiply both sides by delta x and get an equivalent expressions for every pair f of x sub I plus 1 minus f of x sub I. We could replace that with the derivative of f at a z times delta x. So that's going to become very important. We're going to be able to take this value and plunk it in over here, because these expressions are the same. This was the result from our second fundamental theorem video. This is what we got. But now we can combine that with our algebra trick. We are doing that replacement. What we said was equal to this expression is this derivative times delta x. So it's equal to f of b minus f of a. You have to make sure you're comfortable with that. You may want to pause the video and go back. These are equal. And then, because our operating assumption is the derivative of capital F is lowercase f, I can do a substitution. But then we have to realize we've satisfied the definition of the integral. Notice that I've put two operations here just so you understand that they're equivalent. When delta x is going to 0, n is going to infinity. So I've put them both here so you think of them both together. But this is the integral from x sub 0 to x sub n of f of x dx. So what does that say? That says that these are equal. Isn't that what we're trying to prove? Our mean value theorem expression is equal to this expression with lowercase f, which is the integral of f. So since these are equal, and these are equal, these are equal. It's transitivity. You might want to go over this, you might want to pause here and go over this several times, because this is the core of the fundamental theorem of calculus. This is a huge accomplishment. And now you have to ask yourself, did we do it? Are you sure? See if you can explain it to yourself.